This photo shows many different pairs of shoes in various colors. The shoes appear to be hanging from a wall by cords, figure 6. If you ask enough people about their shoe size, you will find that your graph data is shaped like a bell curve and can be described as normally distributed. Credit, modification of work, shoe shop by low flicker, public domain, the normal probability density function. A continuous distribution is the most important of all the distributions. It is widely used and even more widely abused. Its graph is bell-shaped. You see the bell curve in almost all disciplines. Some of these include psychology, business, economics, the sciences, nursing, and of course mathematics. Some of your instructors may use the normal distribution to help determine your grade. Most IQ scores are normally distributed. Often real estate prices fit a normal distribution. The normal distribution is extremely important, but it cannot be applied to everything in the real world. Remember here that we are still talking about the distribution of population data. This is a discussion of probability, and thus it is the population data that may be normally distributed. And if it is, then this is how we can find probabilities of specific events, just as we did for population data that may be binomially distributed or Poisson distributed. This caution is here because in the next chapter, we will see that the normal distribution describes something very different from raw data and forms the foundation of inferential statistics. The normal distribution has two parameters, two numerical descriptive measures, the mean mu and the standard deviation sigma. If x is a quantity to be measured that has a normal distribution with mean mu and standard deviation sigma, we designate this by writing the following formula of the normal probability density function. This is a frequency curve for a normal distribution. It shows a single peak in the center with the curve tapering down to the horizontal axis on each side. The distribution is symmetrical. It represents the random variable x having a normal distribution with a mean, m, and standard deviation. As figure 6.2, the probability density function is a rather complicated mathematical function. Do not memorize it, it is not necessary. Letter 1d453, letter 1d465 equals 1 letter 1d70 e squared 2 letter 1d70b, e minus 1 2 letter 1d465 minus letter 1d707 letter 1d70e. 2. The curve is symmetric about a vertical line drawn through the mean mu. The mean is the same as the median, which is the same as the mode, because the graph is symmetric about mu. As the notation indicates, the normal distribution depends only on the mean and the standard deviation. Note that this is unlike several probability density functions we have already studied, such as the Poisson, where the mean is equal to letter 1d707 and the standard deviation simply the square root of the mean, or the binomial, where p is used to determine both the mean and standard deviation. Since the area under the curve must equal 1, a change in the standard deviation sigma causes a change in the shape of the normal curve. The curve becomes fatter and wider or skinnier and taller depending on sigma. A change in mu causes the graph to shift to the left or right. This means there are an infinite number of normal probability distributions. One of special interest is called the standard normal distribution. The standard normal distribution is a normal distribution of standardized values called z-scores. A z-score is measured in units of the standard deviation. The mean for the standard normal distribution is 0, and the standard deviation is 1. What this does is dramatically simplify the mathematical calculation of probabilities. Take a moment and substitute 0 and 1 in the appropriate places in the above formula, and you can see that the equation collapses into one that can be much more easily solved using integral calculus. The transformation z equals letter 1d465 minus letter 1d707 letter 1d70e produces the distribution z n0, 1. The value x in the given equation comes from a known normal distribution with known mean mu and known standard deviation sigma. The z-score tells how many standard deviations a particular x is away from the mean. Z-scores if x is a normally distributed random variable and xn, mu sigma, then the z-score for a particular x is letter 1d467 equals x letter 1d707 letter 1d70e. The z-score tells you how many standard deviations the value x is above to the right of or below to the left of the mean mu. Values of x that are larger than the mean have positive z-scores, and values of x that are smaller than the mean have negative z-scores. If x equals the mean, then x has a z-score of 0. Example 6. 1. Suppose x n 5, 6. This says that x is a normally distributed random variable with mean mu equals 5 and standard deviation sigma equals 6. Suppose x equals 17. Then letter 1d467 equals letter 1d465 letter 1d707 letter 1d70e equals 1756 equals 2. This means that x equals 17 is 2 standard deviations. 2 sigma above or to the right of the mean mu equals 5. Now suppose x equals 1. Then, z equals letter 1 d465, letter 1 d707, letter 1 d70e equals 156 equals 0. 67 rounded to two decimal places, this means that x equals 1 is 0. 67 standard deviations 0. 67 sigma below or to the left of the mean mu equals 5, try it 6. 1 fill in the blanks. Jerome averages 16 points a game with a standard deviation of 4 points. X ends 16-4. Suppose Jerome scores 10 points in a game. The z-score when x equals 10 is 1,5. This score tells you that x equals 10 is standard deviations to the right or left of the mean. What is the mean? The empirical rule: if x is a random variable and has a normal distribution with mean micro and standard deviation sigma, then the empirical rule states the following. About 68% of the x values lie between 1 sigma and plus 1 sigma of the mean micro, within 1 standard deviation of the mean. About 95% of the x values lie between 2 sigma and plus 2 sigma of the mean micro, within 2 standard deviations of the mean. About 99.7% of the x values lie between 3 sigma and plus 3 sigma of the mean micro, within 3 standard deviations of the mean. Notice that almost all the x values lie within 3 standard deviations of the mean. The z-scores for plus 1 sigma and 1 sigma are plus 1 and 1 respectively. The z-scores for plus 2 sigma and 2 sigma are plus 2 and 2 respectively. The z-scores for plus 3 sigma and 3 sigma are plus 3 and 3 respectively. This frequency curve illustrates the empirical rule. The normal curve is shown over a horizontal axis. The axis is labeled with points s, -2s, -1s, m1s, 2s, 3s. Vertical lines connect the axis to the curve at each labeled point. The peak of the curve aligns with the point M, figure 6. 3 example 6.2. Suppose x has a normal distribution with mean 50 and standard deviation 6. About 68% of the x values lie within 1 standard deviation of the mean. Therefore, about 68% of the x values lie between 1 sigma equals 1, 6 equals 6 and 1 sigma equals 1, 6 equals 6 of the mean 50. The values 56 equals 44 and 50 plus 6 equals 56 are within 1 standard deviation from the mean 50. The z-scores are 1 and plus 1 for 44 and 56, respectively. About 95% of the x values lie within 2 standard deviations of the mean. Therefore, about 95% of the x values lie between 2 sigma equals 2, 6 equals 12 and 2 sigma equals 2, 6 equals 12. The values 50, 12 equals 38 and 50 plus 12 equals 62 are within 2 standard deviations from the mean 50. The z-scores are 2 and plus 2 for 38 and 62, respectively. About 99.7% of the x values lie within 3 standard deviations of the mean. Therefore, about 99.7% of the x values lie between 3 sigma equals 3, 6 equals 18 and 3 sigma equals 3, 6 equals 18 of the mean 50. The values 50, 18 equals 32 and 50 plus 18 equals 68 are within 3 standard deviations from the mean 50. The z-scores are 3 and plus 3 for 32 and 68, respectively. Try it 6.2. Suppose x has a normal distribution with mean 25 and standard deviation 5. Between what values of x do 68% of the values lie? The shaded area in the following graph indicates the area to the right of x. This area is represented by the probability p(x)(x). Normal tables provide the probability between the mean, 0 for the standard normal distribution, and a specific value such as x1. This is the unshaded part of the graph from the mean to x1. This is a normal distribution curve. A value x is labeled on the horizontal axis x. A vertical line extends from point x to the curve, and the area under the curve to the left of x is shaded. The area of this shaded section represents the probability that a value of the variable is less than x, figure 6. 4. Because the normal distribution is symmetrical. If x1 were the same distance to the left of the mean, the area, probability in the left tail, would be the same as the shaded area in the right tail. Also, bear in mind that because of the symmetry of this distribution, 1/2 of the probability is to the right of the mean and 1/2 is to the left of the mean. Calculations of probabilities: to find the probability for probability density functions with a continuous random variable, we need to calculate the area under the function across the values of x we are interested in. For the normal distribution, this seems a difficult task given the complexity of the formula. There is, however, a simple way to get what we want. Here again is the formula for the normal distribution. Letter 1 d453, letter 1 d465, equals 1 letter 1 d70 e squared 2 letter 1 d70b, e minus 1 2, letter 1 d465 minus letter 1 d707, letter 1 d70e. 2. Looking at the formula for the normal distribution, it is not clear just how we are going to solve for the probability doing it the same way we did it with the previous probability functions. There we put the data into the formula and did the math. To solve this puzzle, we start knowing that the area under a probability density function is the probability. Figure 6. 5. This shows that the area between x1 and x2 is the probability as stated in the formula. P, x1 less or equal to x less or equal to x2. The mathematical tool needed to find the area under a curve is integral calculus. The integral of the normal probability density function between the 2 points x1 and x2 is the area under the curve between these 2 points, and is the probability between these 2 points. Doing these integrals is no fun and can be very time-consuming. But now, remembering that there are an infinite number of normal distributions out there, we can consider the one with a mean of 0 and a standard deviation of 1. This particular normal distribution is given the name standard normal distribution. Putting these values into the formula, it reduces to a very simple equation. We can now quite easily calculate all probabilities for any value of x for this particular normal distribution that has a mean of 0 and a standard deviation of 1. These have been produced and are available here in the appendix to the text or everywhere on the web. They are presented in various ways. The table in this text is the most common presentation and is set up with probabilities for 1/2 the distribution beginning with 0, the mean, and moving outward. The shaded area in the graph at the top of the table in statistical tables represents the probability from 0 to the specific z-value noted on the horizontal axis, z. The only problem is that even with this table, it would be a ridiculous coincidence that our data had a mean of 0 and a standard deviation of 1. The solution is to convert the distribution we have with its mean and standard deviation to this new standard normal distribution. The standard normal has a random variable called z using the standard normal table, typically called the normal table, to find the probability of one standard deviation. Go to the z column, reading down to 1, 0, and then read at column 0. That number 0, 3413 is the probability from 0 to 1 standard deviation. At the top of the table is the shaded area in the distribution, which is the probability for 1 standard deviation. The table has solved our integral calculus problem, but only if our data has a mean of 0 and a standard deviation of 1. However, the essential point here is the probability for 1 standard deviation on one normal distribution is the same on every normal distribution. If the population data set has a mean of 10 and a standard deviation of 5, then the probability from 10 to 15, 1 standard deviation, is the same as from 0 to 1, 1 standard deviation on the standard normal distribution. To compute probabilities, areas, for any normal distribution, we need only to convert the particular normal distribution to the standard normal distribution and look up the answer in the tables. As review, here again is the standardizing formula. Letter 1d440 equals letter 1d465 minus letter 1d707 sigma, where z is the value on the standard normal distribution. X is the value from a normal distribution one wishes to convert to the standard normal. Mu and sigma are respectively the mean and standard deviation of that population. Note that the equation uses mu and sigma, which denotes population parameters. This is still dealing with probability, so we always are dealing with the population, with known parameter values and a known distribution. It is also important to note that because the normal distribution is symmetrical, it does not matter if the z-score is positive or negative when calculating a probability. One standard deviation to the left negative z-score covers the same area as one standard deviation to the right positive z-score. This fact is why the standard normal tables do not provide areas for the left side of the distribution. Because of this symmetry, the z-score formula is sometimes written as letter 1d440 equals letter 1d465 minus letter 1d707 letter 1d70e, where the vertical lines in the equation means the absolute value of the number. What the standardizing formula is really doing is computing the number of standard deviations x is from the mean of its own distribution. The standardizing formula and the concept of counting standard deviations from the mean is the secret of all that we will do in this statistics class. The reason this is true is that all of statistics boils down to variation, and the counting of standard deviations is a measure of variation. This formula, in many disguises, will reappear over and over throughout this course. Example 6. 3. The final exam scores in a statistics class were normally distributed with a mean of 63 and a standard deviation of 5. Problem A. Find the probability that a randomly selected student scored more than 65 on the exam. B. Find the probability that a randomly selected student scored less than 85. Solution A. Let x equals a score on the final exam. Xn 63.5, where mu equals 63 and sigma equals 5. Draw a graph, then find px 65, px 65 equals 0. 3446. This is a normal distribution curve. The peak of the curve coincides with the point 63 on the horizontal axis. The point 65 is also labeled. A vertical line extends from point 65 to the curve. The probability area to the right of 65 is shaded. It is equal to 0. 3446, figure 6. 6 letter 1 D44D 1 equals letter 1 D465 1 minus letter 1 D707 letter 1 D70E equals 65 minus 63 equals 0. For px greater or equal to x1 equals pz greater or equal to z1 equals 0. 3446 the probability that any student selected at random scores more than 65 is 0. 3446, here is how we found this answer. The normal table provides probabilities from 0 to the value z1. For this problem, the question can be written as px greater or equal to 65 equals pz greater or equal to z1, which is the area in the tail. To find this area, the formula would be 0.5 px less or equal to 65. 1/2 of the probability is above the mean value because this is a symmetrical distribution. The graph shows how to find the area in the tail by subtracting that portion from the mean 0 to the z1 value. The final answer is px greater or equal to 63 equals pz greater or equal to 0.4 equals 0. 3446z equals 65 63 equals 0. For area to the left of z1 to the mean of 0 is 0. 1554 p x 65 equals pz04 equals 0.5 0. 1554 equals 0. 3446 problem solution bz equals letter 1 d465 minus letter 1 d707 letter 1 d70e equals 85 minus 63 equals 4. 4 which is larger than the maximum value on the standard normal table. Therefore, the probability that one student scores less than 85 is approximately 1 or 100%. A score of 85 is 4. 4 standard deviations from the mean of 63, which is beyond the range of the standard normal table. Therefore, the probability that one student scores less than 85 is approximately 1 or 100%. Try at 6.3, the golf scores for a school team were normally distributed with a mean of 68 and a standard deviation of 3. Find the probability that a randomly selected golfer scored less than 65. Example 6. For a personal computer is used for office work at home, research, communication, personal finances, education, entertainment, social networking, and a myriad of other things. Suppose that the average number of hours a household personal computer is used for entertainment is 2 hours per day. Assume the times for entertainment are normally distributed and the standard deviation for the times is half an hour. Problem A. Find the probability that a household personal computer is used for entertainment between 18 and 275 hours per day. Solution A. Let x equals the amount of time in hours a household personal computer is used for entertainment. xn205 where mu equals 2 and sigma equals 0.5. Find p1 8x2. 75. The probability for which you are looking is the area between x equals 18 and x equals 275. p1 8x275 equals 0. 5886. This is a normal distribution curve. The peak of the curve coincides with the point 2 on the horizontal axis. The values 18 and 275 are also labeled on the x-axis. Vertical lines extend from 18 and 275 to the curve. The area between the lines is shaded. Figure 6.7 p1 8 less or equal to x less or equal to 2. 75 equals p xi less or equal to z less or equal to z2. The probability that a household personal computer is used between 18 and 275 hours per day for entertainment is 0. 5886. Problem B. Find the maximum number of hours per day that the bottom quartile of households uses a personal computer for entertainment. Solution B. To find the maximum number of hours per day that the bottom quartile of households uses a personal computer for entertainment, find the 25th percentile, k, where pxk equals 0.25. This is a normal distribution curve. The area under the left tail of the curve is shaded. The shaded area shows that the probability that x is less than k is 0.25. It follows that k equals 167, figure 6. 8 letter 1 d453 letter 1 d44d equals 0, 5 minus 0, 25 equals 0, 25 therefore z approximately minus 0, 675 or just 0. 67 using the table, letter 1 d44d equals letter 1 d465 minus letter 1 d707, letter 1 d70e equals letter 1 d465 minus 20. 5 equals minus 0. 675 therefore x equals minus 0, 675 asterisk 0, 5 plus 2 equals 1, 66 hours. The maximum number of hours per day that the bottom quartile of households uses a personal computer for entertainment is 166 hours. Try it 6. 4. The golf scores for a school team were normally distributed with a mean of 68 and a standard deviation of 3. Find the probability that a golfer scored between 66 and 70. Example 6.5. In the United States, the ages 13 to 55 plus of smartphone users approximately follow a normal distribution with approximate mean and standard deviation of 36. 9 years and 13 9 years, respectively. Problem A. Determine the probability that a random smartphone user in the age range 13 to 55 plus is between 23 and 64 7 years old. Solution A0. 8186. Problem B. Determine the probability that a randomly selected smartphone user in the age range 13 to 55 plus is at most 58 years old. Solution B0. 8413. Try it 6.5. Use the information in example 6.5 to answer the following questions. Find the 30th percentile and interpret it in a complete sentence. What is the probability that the age of a randomly selected smartphone user in the range 13 to 55 plus is less than 27 years old? Example 6. 6. A citrus farmer who grows mandarin oranges finds that the diameters of mandarin oranges harvested on their farm follow a normal distribution with a mean diameter of 5.85 cm and a standard deviation of 0.24 cm. Problem A. Find the probability that a randomly selected mandarin orange from this farm has a diameter larger than 60 cm. Sketch the graph. Solution. This is a normal distribution curve. The peak of the curve coincides with the point 2 on the horizontal axis. The values 1, 8, and 2, 75 are also labeled on the x-axis. Vertical lines extend from 1, 8, and 275 to the curve. The area between the lines is shaded. Figure 6 9. Letter 1 D4 4 D1 equals 6 minus 5. 85 24 equals 625 p x greater or equal to 6 equals p z greater or equal to 0 625 equals 0 2670 b. The middle 20% of mandarin oranges from this farm have diameters between and equals 0 22 equals 0 10, therefore z approximately plus 0. 25 z equals letter 1 d465 minus letter 1 d707 letter 1 d70 equals letter 1 d465 minus 5. 85 0. 24 equals plus 0. 25 right plus 0. 25 0. 24 plus 5. 85 equals 5. 795 91. Try it 6. 6. Using the information from example 6.6, answer the following. The middle 40% of mandarin oranges from this farm are between and find the 16th percentile and interpret it in a complete sentence. We found earlier that various probability density functions are the limiting distributions of others. Thus, we can estimate one with another under certain circumstances. We will find here that the normal distribution can be used to estimate a binomial process. The Poisson was used to estimate the binomial previously, and the binomial was used to estimate the hypergeometric distribution. In the case of the relationship between the hypergeometric distribution and the binomial, we had to recognize that a binomial process assumes that the probability of a success remains constant from trial to trial. A head on the last flip cannot have an effect on the probability of a head on the next flip. In the hypergeometric distribution, this is the essence of the question, because the experiment assumes that any draw is without replacement. If one draws without replacement, then all subsequent draws are conditional probabilities. We found that if the hypergeometric experiment draws only a small percentage of the total objects, then we can ignore the impact on the probability from draw to draw. Imagine that there are 312 cards in a deck comprised of 6 normal decks. If the experiment called for drawing only 10 cards, less than 5% of the total, then we will accept the binomial estimate of the probability, even though this is actually a hypergeometric distribution because the cards are presumably drawn without replacement. The Poisson likewise was considered an appropriate estimate of the binomial under certain circumstances. In random discrete variables, we found that if the number of trials of interest is large and the probability of success is small, such that letter 1d707 equals letter 1d45b letter 1d45d7, the Poisson can be used to estimate the binomial with good results. Again, these rules of thumb do not in any way claim that the actual probability is what the estimate determines, only that the difference is in the third or fourth decimal and is thus de minimis. Here again, we find that the normal distribution makes particularly accurate estimates of a binomial process under certain circumstances. Figure 610 is a frequency distribution of a binomial process for the experiment of flipping 3 coins where the random variable is the number of heads. The sample space is listed below the distribution. The experiment assumed that the probability of a success is 0.5. The probability of a failure, a tail, is thus also 0.5. In observing figure 6.10, we are struck by the fact that the distribution is symmetrical. The root of this result is that the probabilities of success and failure are the same, 0, 5. If the probability of success were smaller than 0, 5, the distribution becomes skewed right. Indeed, as the probability of success diminishes, the degree of skewness increases. If the probability of success increases from 0, 5, then the skewness increases in the lower tail, resulting in a left-skewed distribution. A histogram showing the frequency distribution of flipping 3 coins, where x represents the number of heads. The vertical y-axis represents probability. Each bar has a label on the horizontal axis in the center of the bar. The labels are 0, 1, 2, 3. The height of the bar representing 0 heads is 1, 8. The height of the bar representing 1 head is 3, 8. The height of the bar representing 2 heads is 3, 8. The height of the bar representing 3 heads is 1, 8. Below the histogram is the set S representing the sample space. The elements of the set are HHH, HHT, HTH, THH, TTT, TTH, THT, HTT, figure 6. 10. The reason the skewness of the binomial distribution is important is because if it is to be estimated with a normal distribution, then we need to recognize that the normal distribution is symmetrical. The closer the underlying binomial distribution is to being symmetrical, the better the estimate that is produced by the normal distribution. Figure 6.11 shows a symmetrical normal distribution transposed on a graph of a binomial distribution where p equals 0. 2 and n equals 5. The discrepancy between the estimated probability using a normal distribution and the probability of the original binomial distribution is apparent. The criteria for using a normal distribution to estimate a binomial thus addresses this problem by requiring both np and n, 1 minus p, are greater than 5. Again, this is a rule of thumb, but is effective and results in acceptable estimates of the binomial probability. A histogram showing the frequency distribution of a binomial distribution with p equals 0. 2 and n equals 5. The random variable x represents number of heads. The vertical y-axis represents probability px. Each bar has a label on the horizontal axis in the center of the bar. The labels are 0, 1, 2, 3, 4, 5. The height of the bar at 0 is 0. 3277. The height of the bar at 1 is 0. 4096. The height of the bar at 2 is 0. 2048. The height of the bar at 3 is 0. 512. The height of the bar at 4 is 0. 64. The height of the bar at 5 is 0. 3. Superimposed on the histogram is a normal distribution curve with mean mu equals 1. Figure 6.11 example 6.7. Imagine that it is known that only 10% of Australian Shepherd puppies are born with what is called perfect symmetry in their 3 colors, black, white, and copper. Perfect symmetry is defined as equal coverage on all parts of the dog when looked at in the face and measuring left and right down the center line. A kennel would have a good reputation for breeding Australian Shepherds if they had a high percentage of dogs that met this criterion. During the past 5 years and out of the 100 dogs born to Dundee kennels, 16 were born with this coloring characteristic. Problem: what is the probability that in 100 births, more than 16 would have this characteristic? Solution: if we assume that one dog's coloring is independent of other dogs' coloring, a bit of a brave assumption, this becomes a classic binomial probability problem. The statement of the probability requested is 1 minus p, x equals 0, plus p, x equals 1, p, x equals 2 plus p, x equals 16. This requires us to calculate 17 binomial formulas and add them together and then subtract from 1 to get the right-hand part of the distribution. Alternatively, we can use the normal distribution to get an acceptable answer and in much less time. First, we need to check if the binomial distribution is symmetrical enough to use the normal distribution. We know that the binomial for this problem is skewed because the probability of success, 0. 1, is not the same as the probability of failure, 0, 9. Nevertheless, both NP equals 10 and letter 1d45b, 1 minus letter 1d45d, equals 90 are larger than 5, the cutoff for using the normal distribution to estimate the binomial. Figure 6.12 below shows the binomial distribution and marks the area we wish to know. The mean of the binomial 10 is also marked, and the standard deviation is written on the side of the graph. Sigma equals square root letter 1d45b letter 1d45d letter 1d45e equals 3. The area under the distribution from 0 to 16 is the probability requested and has been shaded in. Below the binomial distribution is a normal distribution to be used to estimate this probability. That probability has also been shaded. A histogram showing the frequency distribution of a binomial distribution with p equals 0. 1 and n equals 100. The random variable x represents number of successes. The vertical y-axis represents probability px. The bars greater than 16 are shaded. Below the histogram is the graph of a normal distribution with mean m equals 10. The area under the curve for x16 is shaded, corresponding to the shaded area on the histogram above. Below the graph of the normal curve is the z-score formula. Z1 equals x mu slash sigma in the calculation, Z1 equals 1610 slash 3 equals 2, figure 6. 12 standardizing from the binomial to the normal distribution as done in the past shows, where we are asking for the probability from 16 to positive infinity, or 100 in this case. We need to calculate the number of standard deviations 16 is away from the mean. 10. Letter 1D44D equals letter 1D465 minus letter 1D707 letter 1D70 equals 16 minus 10 3 equals 2. We are asking for the probability beyond 2 standard deviations, a very unlikely event. We look up 2 standard deviations in the standard normal table and find the area from 0 to 2 standard deviations is 0. 4772. We are interested in the tail, however, so we subtract 0. 4772 from 0, 5, and thus find the area in the tail. Our conclusion is the probability of a kennel having 16 dogs with perfect symmetry is 0. 228. Dundee Kennels has an extraordinary record in this regard. Mathematically, we write this as 1 minus letter 1D45D, letter 1D44B equals 0 plus letter 1D45D, letter 1D44B equals 1, plus letter 1D45D, letter 1D44B equals 2 plus letter 1D45D, letter 1D44B equals 16 equals letter 1D45D, letter 1D44B 16 equals letter 1D45D, letter 1D442 equals 0. 228 try at 6. 7. Let's assume that only 10% of the wooden furniture made by a carpenter is made to the exact dimensions in the blueprint. During the last 3 years, the carpenter has made 100 pieces of wooden furniture, and 16 were found to be made to the exact dimensions in the blueprint. What is the probability that, in 100 wooden furniture items, more than 16 would be made to the exact dimensions of the blueprint?